So here we go. Here's our first example. Find the general solution near x equals 0 of y double prime minus xy prime plus 2y equals 0 with initial conditions y0 is 1 and y prime of 0 is 2. I have a notion we'll be filling those in at the very end. So what do we do? Well, this is an ordinary point. X equals any number is an ordinary point for this one. See, because there's no place where the denominators are 0 or any place where things undefined. But it's still simpler to work with power series centered at x equals 0, so let's just do that. If it was centered somewhere else, it would be wise to translate the problem by substituting t equals x minus x0. See, that would make it into a simpler one like this, instead of having to have like this. Instead of x cubed, it would be x minus x of 0 cubed or something like that. And so this is much simpler. So let's work with this one here. And if we differentiate it twice, the first derivative is just c1 plus 2c2x plus 3c3x squared, etc., 4c4x to the third. And y double prime, here's the second derivative. Okay, it means take the first derivative of this. First derivative of c1 is 0. The first derivative of this term is 2c2, see? First derivative of this term is 6c3, and then we can say this is 3 times 4 c4x squared, and keep on going up the line like that. 20 would be, you know, for the next term, which I didn't write, but the first derivative would be 5c5x to the fourth, and if you take another derivative of that, you get 20c5x to the third. So substituting the function as derivatives into the original equation, and that's going to be a little bit painful, but not too painful. It's not so painful as much as it had so much. It was so long. Yes, it was very long, so I couldn't fit it on one line. I put it here. Here's the y double prime, and then minus x times y prime. So here's the y prime, here's the x, and then plus 2y. Well, this is 2 times the y, and that equals 0. So, well, now it's going to get complicated. That means, let's look at the constants here. C2 plus 2c2 plus 2c0 has to be 0, right? And if you look at the x term, we got 6c3 plus c minus c1 plus 2c1. So that's 6c3 plus c1 times x, right? Now let's look at the x squared term from this big equation up here. We got x squared. Let me see. Over here we have 12c4. And here we have negative 2c2, and look, here we have positive 2c2, so they cancel out. We just get negative 12c4 times x squared. X cubed, well, let's see, we got 20c5 and minus 3c3 and then plus 2c3, so that would be 20c5 minus c3, and we will keep doing this, and notice it fits this nice pattern. X to the n times n minus 1 times n minus 2 times c sub n plus 2 minus n times c sub n plus 2c sub n, and that equals 0. Now, time out on this. You see where this came from? This was like the 5 times 4 c5 here. See that? There's the c5. 5 times 4, because, you know, I took two derivatives, so it's going to be, this is the first derivative, this is the second derivative. That's the way it works. And this NCN, well, recall that would be from this part. Here's the NCN, right? Because this power and the subscript are equal from the first derivative. And then finally, this is from the constant part. And so that makes it looks hard. It does. But it's not that hard.
You'll be sorry you did this.
Oh no, I won't at all. It's not that bad. So anyway, we learned from that the 2c2 minus 2c0 is 0, 6c3 plus c1 equals 0, 12c4 equals 0, 20c5 minus c3 equals 0. In the general term, this general term, all this equals 0. So therefore, I have a recursive way by solving for c sub n2. See? I have a recursive way of picking the one that's 2 away from the one that's current. I can pick the numbers out of that now. That's not so bad. So that gives us the recurrence relationship that we're needing. Of course, C2 equals negative C0 from this. C3 equals negative 1/6 of C1. Well, good. This is starting to give me some of the numbers I need. 12C4 has no choice but to be 0, so therefore C4 must be 0. Remember, why does it have to be 0? Because this whole thing adds up to 0, right? So the C4 coefficients have to add up to 0. So we're getting some of these worked out. And listen, once that happens, once we get a 0 here, then all the ones that are odd, C6, C8, C10, C12, they're all going to be 0 because they're going to be some constant times 0. So now C5 is 1/20th of C3, and that's negative 1/120th of C1. So look, C7, 3/42, because if we know what C5 is, it's negative 1/120 C1. Well, C7 is 7 minus, no, sorry. If this is 7, then n is 5. So 5 minus 2 over 6 times 7 times C5. So 3/42 C5. But C5, recall, was some number times C3. What was it times C3? Where's C5? Oh, here it is, 1/20th C3. So then it gets an extra 20th in the denominator. But then C3 is negative 120 C1. So if you do all the multiplication on this, actually I let the C5 be multiplied by negative 1 over 120. So take this, multiply by negative 1 over 120, and you will get this times C1. And carefully writing, we got a 2-parameter family. See, we got C0 times 1 plus x squared. Notice that the C0, we just had this one, this term, and really the second term, right? And there's one of them being the positive and one of them being the negative. And then C1, we got, look, all these nice odd powers, and they can be added up. And oh, did I mess that up? I messed that up somewhere. Did I mess that up somewhere? Yes, I did. This should be x to the 5th. This should be x to the 7th. There we go, 7th. And now we got a 2-parameter family of solutions. See, we got this constant times this solution and this other constant times this solution. And we could keep going. We could make this one go out as far as we wanted to. So, and that is what this particular one looks like. And they're all ordinary points. So y2 converges for all x. y1 obviously converges to this. 1 minus x squared is already done. There's nothing else added, so that's converging. It's converging to that. Since it's finite. So defined our C0 and our C1. Recall, this problem was an initial value problem. So y0 is 1 and y prime is 0 is 2. So what do we do from that? Well, we got our solutions. So if y of 0 is 1, then duh, that means put in 0 here for x squared. C1 must be 1. And if you put in well, if you put in 0 here, you don't find anything about C1. But if you look into y prime, see, y prime was, I forget what. Y prime of 0 is 2. So let's see, what would the derivative be? Well, that would make 2C0x plus C1 times 1, look at this, minus a half x squared, minus I don't think that's 1/24 x to the fourth. I think that should be 1/40. Sorry, x to the fourth. I made a mistake when I typed up the file originally. Whoops. And then you can see how that's going to go on. I don't want to divide 5 into 1860, but I think you see how that's going to go. And so what that forces to happen is, if you put in 0, the only thing that's not 0 is C1. See, because you got 0 in this term, 0 in this term, 0 in all these other terms, and this one. So C1 has to be 2. Remember, y prime of 0 is 2. So we've got our C1 and our C0. Our C1 is, C0 is 1, our C1 is 2, and now we have the actual solution to the differential equation. Right there it is. So pretty cool.
Nice work.
Thank you.